Log on, tune in, find out. Another good idea from Cambridge.
Not the final talk this week. I'm very pleased to have young Boman to speak on the way that radon transforms. Thank you.
Thank you very much. It's a pleasure to be here, and it's a pleasure to have the. I'm grateful for this and for the possibility to speak here also. Now I'm going to speak. Okay, I have to learn. Oh yes, it was correct. Yeah, here is a problem, a simple, quite simple-looking problem that I want to talk about. At least it can be, as you see, it can be formulated in very elementary terms. Given is this set positive smooth function m, depending on 3 variables, and from these integrals for a set of xi eta in the neighborhood of the origin, we want to know if this function f is uniquely determined. And it's, as you see, it's assumed to be 0 under this parabola. So these lines, obviously these xi eta parameters, I want this to be on your mind all the time, so I, more or less, so I draw a little picture here. This support of f is here, and these lines this is a line determined by xi and eta. These lines, when xi eta runs through a neighborhood of the origin, they certainly cover a neighborhood of the origin here. So it might be possible to determine f from this. Now, why study this problem? Well, of course, it's a very local Radon transform with extremely limited data, you can say. And everybody knows now that the problem to determine a function from in space or in a domain in the plane from a lot of its integrals is an important inverse problem. And now I'm going to think about this in a theoretical way. There will be no reconstruction algorithm and no numerical experiments here. I'm interested in the problem whether the function is uniquely determined by the data. And now in many results on this are known, and in many cases the arguments are global. But the global arguments are often more complicated in some way. So I wanted, for a while, I began to study a little more systematically when can one prove uniqueness by only local argument. So this is the problem. And now, well, just as a background, everybody knows that the uniqueness has been known at least from Radon's paper in 1917, and here is even the inversion formula. And I'm not going to use very much this notation, but anyway, as you know, R star here is the mean of the function phi, which is defined on the set of planes or lines that pass through the point. Okay, this well-known theorem, I'm considering only a special case of Helgason's important theorem, as you probably know, also treats the case when the function is defined in the whole space, and the important assumption is that it decays very rapidly, but that's not our concern here. So in the special case when this function is assumed from the beginning to have compact support, his theorem implies this. But Helgason's, that is that if the integral over all hyperplanes that not intersect this compact convex set are 0, then the function has to be 0 outside the set. But Helgason's arguments, if you remember, are not local arguments. He reduces the, well, he observes first that it's enough to prove the theorem for balls, and placing the ball with center at the origin, he takes mean over the angular variable, thereby reducing the problem to one variable problem. So the argument is really not local. But here is a local theorem. Following Bill Rundle's suggestion the other day, I'm going to give you one theorem with a full proof. And this is, is the one. It concerns, now I should have said this, we are still talking about the case when the weight function m is constant, equal to 1. So we actually have a local theorem. And this is stronger than the special case of Helgason's theorem that I showed you, because it implies it, not vice versa. And how is it proved? Can one see everything? Yes, one can. Well, Strichard defines this function gk of xi and eta by taking the same Radon transform of f multiplied by some power of x, as you can see. We are going to prove that all these functions are identical to 0, assuming that Rf is 0. You see that g sub 0 is Rf. That will immediately imply what we want. And how is that proved? Well, differentiating g0, which is Rf, by xi, you see that comes out a little x, because xi is in front of the x. But the same expression is obtained if we differentiate by eta, the g1 by eta. So therefore, delta eta of g1 is the same as delta xi of g0. But it's useful, you know, all these are 0 when if the line doesn't meet the support. That is, if eta is sufficiently negative. So knowing that delta eta of g1 is 0, that is the function g1 is independent of eta, we immediately conclude that g1 is 0, since we know that for negative eta, sufficiently negative eta, it's all 0. So therefore, therefore g1 is 0. Yes. And that process can be continued, because that this equation there, let's see if I can use, yeah, to see is valid with the same argument. And so we obtain gk is identical to 0 in the neighborhood of the origin, of course, for all k. And in particular, if we put c equal to 0, we get this equation, which this equality here, identity here, which says that the restriction of f to a horizontal line is orthogonal to every power of x, hence 0. So now, before I continue, I'm going to show you a couple of other results concerning the local problem. Well, Todd Quinto and I observed long ago that technique that was well known in PDE theory could be used here as long as the weight function is positive and real analytic. And I'm not going to go deep into that. I'm not even going to tell you the definition of the analytic wavefront zero here, wavefront set here, because I'm not going to use it later. It's not at all be essential later. So just briefly, the really essential thing here with some depth in it, which is taken from PDE theory, is the first line, which says that if the Radon transform is 0 in a neighborhood of a line, then all conormals to that line. I'm denoting here the point x, y by z, just to, and theta are the cotangent vectors. So all if Rf to 0 in a neighborhood of some fixed line, say, call it L, then all those conormals, theta plus minus theta, are not in the analytic wavefront set of F. And this is essentially the microlocal regularity theorem for elliptic pseudo-differential operators with analytic elliptic partial differential operators with analytic coefficients, generalized pseudo-differential operators. But the rest is very easy. By the definition of the analytic wavefront set, the analytic wavefront set is preserved after multiplication by a real analytic function. So we get this next line here. Yeah, I don't think it's so necessary to use this, but now I know how to use it if I want. For every real analytic H. And now again, this if it's specialized by choosing C equal to 0, we get that also using more or less the definition of the analytic wavefront set, that the integral as a function of eta here must be real analytic. This is more or less follows from the definition of the analytic wavefront set, since the conormals to the lines were not in the analytic wavefront set. So, and since this function is 0 for negative eta, it must be identically 0, and since it's true for all real analytic H, F must be 0. So that was also known for some time. Now, in the 90s, if I remember right, we have a person here who can correct me if I remember wrong. I think already in the 80s one began to use the spect, it's sometimes called. Although one, I'll explain briefly since I don't think everybody knows. In this case, it's an emission intensity that one wants to determine. And one measures, in medicine, one injects radioactive substance into the blood of the patient, and that emission radiation is measured by means of collimators like that. And so if this is a detector, it seems for a moment that this leads to the same problem, because the detector here will pick up radiation from one line, and so it seems it will measure the integral of the unknown intensity distribution over that line. But this radiation is attenuated, so the emission here is contributing less to that measurement than emission radiation from here. And in mathematically one and also in practice, usually one assumes the attenuation here to be known, and from it one can compute the density weight function m, and it will be like that. And the thing to observe, if you haven't heard about this problem before, is that these these weight functions must be special in some sense, since m depends on 3 variables and it's computed from a function of 2 variables. So the mathematical problem then was to prove that this Radon transform is globally, of course, injective. And the embarrassing fact for mathematicians was that quite a while this procedure was used in hospital, although nobody had proved that it was possible, so to speak. Is that right? More or less.
In a sense, yes.
Yes. So many people, many of us, I too was one of them. Excuse me? Yes?
The attenuation, one would think it depends also on the thing you would want to measure, namely the density of the material, perhaps.
But that's not what one wants to measure here. It's very good you to make it. And here, it's the radiation intensity distribution that is of interest. And sometimes one measures, because since the attenuation influences the Radon transform and hence the inversion, sometimes one measures that first. But as far as I've understood, in many cases it's not that crucial. One knows for the average person.
One wants to find out where the sources will go. Is that right?
Yeah, that's what one wants to know.
Okay.
Because, as far as I know, the main reason that if there are some tumor or other problematic area, the blood will accumulate there, and there is more to it.
Can I make a comment?
Sure.
But now they have these CT SPECT machines, so automatically you can measure the attenuation using CT, which you can use then in your formula to compute M, and therefore then from your emission data you try to reconstruct.
I see, yeah, okay.
So, but sometimes people, you see, this is difficult to do in practice because the SPECT and CT have different specifications. So to convert the CT data to this computer, so sometimes people just use approximate values. For example, if you're in the lung, you know approximately what's the attenuation coefficient, and then you use this approximate value in the reconstruction. But in principle, you can do it now because of this ability to have these CT SPECT machines. In principle, you can do it accurately.
At the same time. Okay. So, yeah, it was therefore at 2001 when it became known that Roman Novikov had come up with not only a uniqueness proof, injectivity proof, but also an explicit formula for this problem. It was a little bit of a sensation, but later it was realized that the work of these 3 Russian people there also implied something similar. And then I wrote down, when I wrote down a couple of names there of people who, after more or less, yeah, all these other were heavily dependent on Novikov's, although the order of appearance of the paper was
What is the name of
Roman Novikov. And when I wrote down these names, I was aware of that there were others that might have been appropriate to put there, and I'm sure I'm reminded of one. Focus should also be there. Because, yeah. Okay, I thought I'd just mention, since the method of proof in my joint paper with Strömberg, it is possible to outline very quickly. I thought I'd mention that, although it's not a local problem. Here is a formula. I don't explain it. Actually, our proof runs as follows. First, well, it's worth mentioning that all proofs that I know of use complex analysis in some way of this. Yeah, one more thing I had planned to say, namely, during this time when I and many others worked on this, trying to prove injectivity for this class of weights, I believed that there was some unknown set of weight functions for which uniqueness holds, but we didn't know, and that I didn't believe that this class of weights had any mathematical significance. So therefore I was quite surprised that when the problem was solved, that more or less exactly this class, the proofs work for this class. So it seems to have some mathematical significance. Anyway, here is what I wanted to say about our proof. The first step, we prove find an inversion formula valid for weight function m that are complex valued and have the very curious property that as for every fixed x as a function of theta. Notice here, the role of theta in the problem is that it's a set of unit vectors in the plane. But now it plays a role of the boundary of the disk in the complex plane. So assuming that this weight function has the property for every fixed x as a function of theta is the boundary value of an analytic function in the disk, then we can find an inversion formula. And then it turns out that every, now we go back to real valued, for every weight function which comes from this problem that I mentioned, the attenuation, attenuated Radon transform, one can, there's a trivial modification of one of this kind. Namely, what do you mean by trivial? Namely, these two factors here, the b and the ax depends only on x. Now x is a point in the plane, x1, x2. And b function depends only on the line. Such factors are trivial because the factor that depends on the line can be moved out of the integral, and the other one can be merged with the unknown function. So that proves the thing. Well, that was a little. Okay, then now we shall, in a couple of minutes, move back to the local. There's no watch in this room. Clock. A couple of years ago, Simon Gindikin came up with an inversion formula for a class of weighted Radon transforms under this condition. And now this condition looked somewhere, I wrote, yeah, here. In these affine coordinates, the condition of the weight for being of this attenuation type can be expressed in the way that if you differentiate along the line, the result is a function that depends only on the line. No, only on the point, actually. So if you take another line through the same point and take derivative along the line, you get the same value. But Gindikin's condition is similar in the sense that, well, where did I write that? yeah, it's dual in a sense. That instead, if you take derivative with respect to the angular variable xi, the result, well, yeah, the result, where is it? At least one of those terms is a function. Well, no, I cannot explain this. Well, anyway, it turns out that if you, one way to say what I was trying to say is that if you compute the adjoint Radon transform, if the weight satisfies Gindiken's condition, the adjoint will be exactly of attenuation type. So it was, the conditions were strongly related, and I was quite puzzled when I saw this, because I thought first, because Gindiken's proof is extremely elementary, there's no complex analysis, no advanced techniques or anything. But after a while, I understood that this is actually a simpler result. It does not imply the other at all. And therefore, I got the idea to try to prove a local statement for this class of weights. And it turned out that I could do that with this simple argument of Strichart's that I mentioned earlier. And the difference will be, I will not go through the formulas, I will just mention in principle what happens. I formed these functions gk, the corresponding Radon transforms of f multiplied by some power of x as before, but now with a weight. And then in trying to do the same thing, that is by differentiating first with respect to xi and then with respect to eta, the difference would be there comes up additional terms because of the presence of the weight function, which are a nuisance because they are not related at all to the Radon transform or its derivatives. But instead of the, you remember what I could prove before was this equation without these. But now I get such a relationship still. And the reason is that when I subtract here, the assumption relates a linear combination of those derivatives with an x in front of the eta derivative to some innocent factor multiplied by m itself. And what do I mean by innocent factor? Yeah, that's a factor that can be moved outside out of the integral. So, okay, that's another story. So let's see, how much time do I have? I thought a little later I will tell you an attempt to extend this further. But first, I thought I'd say a couple of words about this old result of mine, more 20 years old. Yeah, during, and the reason I hope will be clear in a couple of minutes. During the time when many of us struggled to prove uniqueness theorem for this class of attenuated transforms, some colleagues thought that the Radon transform with an plain Radon transform with an arbitrary smooth positive weight function was injective on functions with compact support. I did not believe that, so therefore I proved it is not true. But now, the reason I want to speak a little about that now is that is the following. In the proof of this fact, if you prove that such a Radon transfer is not always locally uniqueness, it's trivial to pass from that to the stronger statement that there exist wave functions which are not globally injective. So I thought a couple of years ago, I got the idea to try to simplify my proof of this counterexample, because I had not many people read the article, I think. Because there are some complicated, well, not really, but rather fairly cumbersome computations there. If I concentrate on the sort of reprove the example, construct and prove for of non-local uniqueness with concentration on the local problem, computations might become simpler. And the reward for doing that was not just a somewhat simplification, but also an extension. And that's what I will tell you the new theorem in a couple of, almost new, in a couple of minutes. So let me review the idea. Well, the idea is to choose the function first and then construct the exceptional weight function for which we don't have local uniqueness. And of course the function, yeah. And you see here, how do I choose? I said a couple of words later about how I choose the function. But the weight function, here is a little perturbation of the constant function by a function, a constant depending only on the line. It's appropriate here to use geometric notation rather than xi and eta, multiplied by some function. And it's not a very big deal here that I use the function f itself here. The only reason is, as you can see, if I form, is that if I multiply it with f, I get something positive. So now what does, or if m is this, or mf becomes this, and I want this to be 0, I can solve c of L, and it becomes that over that. And now the obvious observation, if I want to construct f that is mapped to 0 by such a transform, it has to change sign on every line. So in particular, I want f to, as I said, to be supported in such an angular region. So it has to oscillate extremely fast here. And incidentally, reason for the simplification relative to the earlier construction and proof maybe that the difficulties now are concentrated at one point, really, one point in space. A little curve in the actually on the curve of lines through that point. Because the only difficulty is to prove that the weight function will be smooth. Because with this yeah, let's see how much time I have, a couple of minutes. A little. F is an infinite sum of functions supported in rectangles like that. And you see how this 2 through k here moves the rectangle in this way. and each term is multiplied by something oscillating faster and faster with respect to x. And then I sum all those, and due to the faculty k here, it's trivial that the sum is C infinity. And also those statements are also trivial, and one more is obvious, namely that this, remember, m is 1 minus C of L times f, and f is C infinity. So the only thing we have to prove is that C as a function of xi eta is C infinity. And I'm saying that it's obvious that this is true except at that point, as I said, because because the numerator is certainly smooth with respect to L, except at that point, and the denominator is positive. So there are a number of lemmas, but all are straightforward, except, well, perhaps this one also, but this is a crucial one. I just want to tell you what the key point is, namely that this factor 4 is bigger than 2. So there are very good estimates for the derivatives of the integral of the of f, and each line meets at most 2 of those blocks. And I just show you this, and then I'll go to another problem. Making p partial integrations in the definition of this integral. I have not differentiated yet. This I estimate without differentiation with respect to xi eta first. There comes out p such powers here, coming from here, and there will be p powers of 2 instead, but they can do nothing to those. And it's easy to see that taking differentiation only makes a difference. You have to make more partial integrations. So that is the key point. Now, so I can move over this because it's really trivial. But here is what is. Having done that, it's easy to see that if I insert a little factor here, which I allow to be large, the oscillation will be even faster, and the integrals of f will be even smaller, and this means that the factor CL, which determines how much the constant is perturbed, will become smaller. So in a fixed region, we can make the constructed wave function as close to the constant 1 as we wish in this way. But more interesting, nothing changes if we start with a fixed, arbitrary, smooth positive weight, and instead of 1, and do this. We have shown by the same argument that an arbitrary small perturbation in the C infinity topology of that one also produces, in this way, a weight function for which the local problem is not injective. And that perhaps has some interest because, here is the theorem which I just said. But this should be compared to the situation with global injectivity. You know, if a weighted Radon transform is global weighted Radon transform is injective, then by function analysis there is invertibility in some Sobolev norms, and therefore by standard arguments a little perturbation will also be injective. Just as the set of operators in any algebra is invertible operators in open. So by that we know that the local injectivity problem is different from the global. All right. Yeah, I plan to make some more comments on this, but let me first move to generalization and extension. I thought, considering a purely local problem, it might be good to have a statement that is invariant under coordinate transformations. So I mean, this was really my main goal, not just to obtain a more general statement. I thought one might understand something about the true nature of those assumptions if one has a statement that has some invariance properties. So considering now a more or less arbitrary, quite arbitrary little curve family, just satisfying some non-degenerate conditions of the kind that it's two-parametric family. Non-degenerate in the sense that at every point and at least in some open set, for every point in that and in an open set of directions, at least, there is a unique curve in my family through that point with that tangent direction. Then I can make coordinate changes in the xy space and in the parameter space, so that the curve family looks like that for xi eta close to 0. So it's actually no. I'm just saying that there is no restriction to assume that the family is a small perturbation like that. So then the first thing to do is to convince oneself that one can formulate a problem in an invariant way, and that these people there have taught us long ago how to do that. It's rather interesting. Let me show you if you may not have seen it. Was there something I forgot to say? Yeah. In terms of our coordinates, well, we should think of the space, this neighborhood in the xy space as one abstract manifold, and the space of curves as another abstract manifold. And then this equation defining, it's used to define my curve family, becomes a hypersurface in that product manifold. And if we think abstractly, this is called the incident manifold. It's just, namely, it's perhaps it's written there. It's set of pairs of points and curves such that point is on the curve. And now we get back the curves from the projection. Actually, I should have written here that the projection down to x, for instance, goes from z. So the z should, the hypersurface, I'm explaining how this hypersurface, assuming some non-degeneracy conditions again, which I don't want to mention, gives back the curves, namely the inverse image of the projection down to gamma gives a curve in Z, the hypersurface, consisting of all the x, but p and gamma. If we project it down as here to the x space, we get the curve itself in the x space, and vice versa. The other is the curve in the space of curves, which goes through a given point. Now, yeah, I have a couple of minutes. How to define the Radon transform? Well, we must integrate, so we need a measure. So, corresponding to my weight function, I assume defined a measure on C, which in our coordinates you have to practice this, reads for like that. Now, I'm going to quickly tell you the assumptions that it turned out that I could in this more general situation make another variation of this Strichard's argument, and the conditions that I needed to make looked curious first. So first I was disappointed. As I said, I hoped to understand something by looking at the problem in this more general way. But at this point I felt I understood nothing. But there will be surprises to come. So something seems to be possible to understand. At least, yeah. So here were the conditions in coordinates. Instead of, I forgot, the u used to be called gamma. I'm sorry, I forgot. From the function defined in the curve family is by mistake called gamma here. So from this, I compute this auxiliary function q, which will play the same role as the factor x played earlier. And why does it? Because, you know, taking the derivative of u with respect to c gives x, and with respect to eta gives 1. So just as I say here. So it's natural generalization. So the first condition, if you remember that q is somewhat like x was before, this looks like the earlier condition. And now but in this case I needed a condition on the curve family as expected. And it looked to me first extremely strange. Namely that if I shift the role between x, y, and c eta, which is sometimes useful in this business, it's just another, can be viewed as just another way to define the C surface with eta solved with respect to all the others instead of y. And the assumption is that that this eta as a function of c with x and y as parameters must satisfy such a differential equation, or ordinary differential equation of degree 2 when the right-hand side is a polynomial in the derivative with coefficients in the other variables. And I had never seen this I'm not a differential geometer. I've never seen this assumption on a differential equation. How many of you have seen this? Well, it turned out that, first of all, I should say, first of all, it turned out already in Arnold's book of geometric aspect of differential equation, one can learn that this class of differential equation, where such a polynomial condition is invariant under coordinate transformations. And moreover, it was known by Elie Cartan. So Elie Cartan wrote a paper in 1924 on something which I have not, this is quite recent part of the work, I have not yet learned. He introduced something called projective connections on a manifold.
But there are no assumptions on the dependence on psi and eta, on this psi? I mean, it's polynomial in P. But
No, only smooth, nothing else. Nothing else. He's under certain a special class of such projective connections, which was particularly natural and interesting, turned out to have the property that the geodesics with respect to that connections are exactly those. So that maybe has nothing to do with our problem. I'm not sure, I have to check. But I mention it for historic reasons. But yeah, actually this may be, here, this I wrote to show you that the assumption, I was able to, after experimenting, quite a bit of experiment since I'm not a differential geometer, but I was able to find a formulation, invariant formulation of that condition on the weight, like that. Let's not spend time on it. But this is my last picture. This is a fact that I just mentioned on these differential equations. What I also wanted to say then, that which I think is interesting, but I've not yet have time to pursue, is that those of us who are interested in tomography and integral geometry know that the Russian school, beginning with Gelfand, are very, very far back. Moscow school wrote many papers, important papers on integral geometry, and they came up with an important property of families of curves, or sometimes families of surfaces, admissible families. And the condition in a two-dimensional case for this coincides with my conditions. And what was admissible families? Well, it had to do with, I only say, I'm not going to define it, but at first, as far as I know, the beginning of all this was that Gelfand, in his study of group representations and Fourier analysis on these non-commutative groups, was led to a problem, an integral geometry problem in the complex case. That is, to recover a function in a domain in C3 from integrals over families of complex lines in C3. And in that case, it is possible to obtain local inversion formulas. similarly to, the ordinary Radon transform in odd dimensions in R3 is local. And that actually has to do with that the spaces that we integrate over is even dimension. So the corresponding problem, there is also the problem with applications also to recover a function in R3 from integrals over a set of lines. Now the set of all lines in R3 is a four-dimensional family. So therefore it's interesting to study this problem for submanifolds that are three-dimensional. And it turned out that this concept of, as I said, in the complex case, these nice, these admissible families of lines were precisely those for which there existed a local inversion formula. But it turned out that and there's a huge set of papers on this from in the late 60s and 70s and 80s. But the concept of admissibility, it has to do with, for those who have know a little bit of this famous kappa operator, which is a closed form that has to be closed and is used in these elegant formulas that they derived. This admissibility property has relevance also in the real case, and it seems to be characterized by the same conditions as mine. So this was a little, maybe this can help to understand something, but just now I just think that it's interesting that my completely different problem, this local problem, led to the same conditions. So in the future I hope to understand this a little better, how this is related to all that. Okay, I'll stop here.
Maybe a very elementary question, but it's to do with what you were talking about at the end. In three-dimensional space, if you have weighted integrals along lines starting at a point, so you have attenuated from, you mentioned these three-dimensional families in four-dimensional space. Is there something like the John equation for the attenuator?
Something like the John equation.
The ultra-hyperbolic equation.
You mean the John equation gives us a necessary sufficient on the data function. Yeah, that's what you mean. But you wonder if there is a similar, I don't remember.
For emission,
should be
3D emission.
With weights.
With weights, yeah.
I don't remember that. I don't think so. It's not so simple. If I understand your question, it's related to characterizing the range, isn't it?
Exactly, yeah.
Yes.
Yeah, so the range of the X-ray transform is exactly the null space of the...
No, I don't think there is something like that. No. Mm-hmm.
I have a question on the non-uniqueness result that you showed, the non-injectivity result. Can you generalize the construction of your weights to these curves that you showed us? Can you generalize the non-injectivity result for weighted transforms? A specific example. Why would it not work for curves?
I think so, yes. That should be no problem. I don't know. I plan to say that, to sum up, that there is, in spite of all this work, there is very little we know. It is, in some sense, it's a zero set. Because I only know that the, as I said, that the set of good weight functions for the local problem is dense, because the real analytic are good ones. And I constructed a set of bad ones, which is also dense. But I can never say that the weight function is bad unless it's one that I've constructed for that purpose.
Right, so you believe that the construction would work for curves?
Yes, I think so, yes.
Yeah. Very plausible.
And all the sets of the classes of good ones that we know are zero sets in some sense. Either the real analytic ones or some such that satisfy some differential equation. So there remains something to be understood. I'd say. So therefore, yes.
Would you allow me to make a remark? Historical remark about, thank you.
Yeah,
A very good-
well, for me,
a very quick remark, you see, because you mentioned Gelfand, and certainly Gelfand is really behind this formula of Roman, you see, because in
I didn't know.
yes, that's, so in 1994, we wrote a paper with Gelfand, and this paper will show that if you do the spectral analysis of some equations like this, if you do a spectral analysis of some equation like this, then out of this you get nothing new, because you get two-dimensional Fourier transform using something like a D-bar formulation. And this, we understood at the time that this was maybe a new method to invert integrals. So this is when Novikov was visiting us. So I asked Roman, because I knew he was interested in Radon, to do this technique to invert Radon. So although we wrote this paper with Gelfand in 94, the paper with Roman was in 92. It was earlier, because this paper with Gelfand took a long time to be. So in this paper with Roman, we did nothing new, because we inverted the Radon transform using spectral theory. It was something like this, some slight variation of this equation. And we got the Radon, but of course, because we had to say something new in order to publish it, we also got some discrete Radon. See?
Okay.
But at the time, of course, I didn't know at least that this other problem was open. So what Roman did is he looked exactly at the equation we had in our paper, but he added here one more term, which is Fm, or M, if you want it in your notation. And this, using exactly the same technique, this gave this beautiful formula that Roman got of the numerical dot. And then after I saw this paper, then I realized that this factor, this term actually, using something like, how do you know, the integrating factor, you could map this equation to the one we had before. So in some sense, this is already in our paper, although certainly the first person to write explicitly this formula was Roman. So really, behind all this new development, there was this technique which was introduced really under the influence of Gelfand, of doing spectral theory using non-analytic tools like the bar problems.
Oh.
And this is, in a couple of lines,
That
the
I
story.
did not. That's interesting. Thank you.
And to close the loop, that you mentioned that people were doing emission computed tomography before they knew it could be done.
Yeah.
Yeah, but
And I know some of these people, and they were quite pleased when they saw the paper by Roman Novikov.
Oh,
You know.
interesting.
But yeah, I can also make a remark on this if you want, because this paper has not been used yet in practice. You see, because
Yeah, they do it,
there are two ways. There are two ways that people. Of course, first of all, you say how can you do spect without knowing this inversion? You see, first of all, Brian Wooden, who's a friend of mine, was telling me that he was giving lectures claiming that because of the lack of invariance, the attenuated Radon transform will never be inverted. You will never find an exact formula. So of course he was surprised when Raman gave this. But remember that there are two techniques really to invert, even in practice. One is to use analytical formulae, yes, and the other is to use iterations. You see, a statistical formulae. And still, now the modern machines the modern machines I mentioned earlier, SPECT CT, they give the physician an option. So the option is they can either use an analytical formula, which is pseudo projection, which means that they put f equals 0, so they take the attenuation to be 0. Or they use OSEM, which is the statistical formula. So nobody at this stage uses the numerical implementation of the Raman formula. We're trying to do it, and maybe it will die shortly. But up to this point, the commercial machines give you the option, which is either based on neglecting attenuation, in which case you go back to Radon, and then you use pseudo projection, or you use these iterative approaches which you don't care about in just inversions. So this is why they could do it even without knowing.
Oh, okay.
Even without knowing, because
Are there any further questions right now? If not, then we're not faced with a problem of having to do something we don't know how to do. We know how to go find coffee, so we should.
that's always good.
And thank the speaker for